Ma'am, can you hear me? I couldn't hear you at first.
Yes, Basmi, am I audible to you now?
Yes, ma'am.
Okay. See, we started with this electromagnetic waves and what all things we discussed. Let us just quickly revise them. Okay. Did you go through the
Mm.
notes?
Yes, ma'am.
You went through the notes. Yesterday we didn't have our class. We were not supposed to have a class. By mistake, that meeting was set up because I already told you that
Okay,
we'll
ma'am.
have the class on Saturday because of the
Yes,
holiday. So
ma'am.
there was a little confusion. They thought your class is still there. So that's why your class. Did you join the meeting?
I joined it and then I asked them. They still said yes, there is class. So I was there for
What?
half an hour and then I left.
You?
I was there in the meeting for around 20, 30 minutes and I left.
Okay, you were there around 20 to 20 minutes. All right. So you didn't get any
Yes.
message then that no class is there?
Ma'am, I messaged them and then they said there is still a class. So I stayed.
Okay. Actually, there was a confusion yesterday because of the holiday and all. They thought
Mm.
your class is still there. So because your class was happening in the morning. Though I then told them that there wasn't any class and I was also not there. Otherwise, I would have just texted it if I had known. So I got to know it later that there is a class, and I think after that, 45 minutes were there after the meeting started. So it was a time, by that time, you were already informed that there isn't class. Okay. See, whenever the meeting ID comes, usually we have the classes on that day, but yesterday a little confusion was there regarding the timings, and see, somebody else class was there in the evening, so they thought your class is also there. Okay. So,
Okay, ma'am.
see, we discussed the equation of electric field and magnetic field, that is E naught sine kx plus minus omega t. We'll practice questions based on this. Okay,
Okay, ma'am.
spectrum part I'll discuss. We did certain properties, and the properties was the major
Mm.
part of the yesterday's class. Electric field, magnetic field, and the direction of propagation all are perpendicular to each other. We also saw that the speed of light is the ratio of the electric field and the magnetic field, and the speed of light, electromagnetic wave in any medium is the ratio of the electric field in that medium and magnetic field in that medium. Then we saw the formula of the
Mm.
speed of EM wave. Basically, using the formula, how do we get the actual value of the speed of light? So C is equal to 1 by under root epsilon naught mu naught. Epsilon naught is the permittivity of free space, mu naught is the permeability of free space. So the value that we get is 3 into 10 to the power 8 meter per second. And for any medium, when the EM wave is present in any medium, we get this speed as C by under root mu r into epsilon r, where mu r and epsilon r, they are the relative permittivity and relative permeability respectively. Okay. Then I
Okay, ma'am.
told you that all optical phenomena are due to electric field. Refractive index basically is the ratio of the speed of light in any medium to the speed of light in air to the speed of light in any medium. That's what the refractive index is. So from this you have this relation which tells that the formula of n is 1 by under root mu r into epsilon r. That's not very important, but
Mm.
I've written it so that when you have all the properties together, you will be able to write them. Okay, means you have to mention them.
Okay, ma'am.
And then we saw energy density. This is a very important property, energy density. So electrical energy we saw, magnetic energy we saw. This is the RMS value, half epsilon naught E square and half B square by mu naught. These are the RMS value. When you
Mm.
have to write it in terms of their peak values, so you have to divide them by root 2. So in short, this becomes 1 by 2 because when you square, so that when you multiply 1 by 2 into 1 by 2, that becomes 1 by 4. So 1 by 4 epsilon naught E naught square plus 1 by 4 B naught square by mu naught. See, epsilon naught gets multiplied while mu naught gets divided. All right.
Yes, ma'am.
Now momentum is equal to energy density divided by the speed of light. This we saw, and I told you whenever there's a change in momentum, it doubles because we have the concept of relative velocity. One velocity positive,
Yes, ma'am.
backward velocity negative. So ultimately they get added. Similarly, momentum also, because all these are vector quantity. And last, we saw that energy per unit area per unit time, or power per unit area, is basically intensity. And we discussed two more points, that the EM waves, electromagnetic waves, are neither deflected by the electric fields nor by the magnetic fields, and they do obey the principle of superposition. Superposition we'll study. A basic of superposition we've already studied about the vectors and the forces and electric fields and all. So regarding waves, superposition of waves we'll do again in the wave optics chapter. Okay. So let me
Okay,
start
ma'am.
with this. It is a plane EM wave of frequency 25 megahertz travels in free space along the x-axis. At a particular point in space and time, electric field is given as this. What is the magnetic field at this point? See, electric field, this is a question from your NCRT, okay? 6.3
Okay, ma'am.
a cap volt per meter is the electric field. It says what is the magnetic field, frequency is given, and direction of propagation is along the x-axis. See, if I have the direction of propagation along x-axis, that means this is a cap. Electric field is along j cap. So where do you think the magnetic field will be? Along which axis?
Take up.
What?
Mm.
Your voice is coming very
Mm.
low today, Basmi. What happened? Just check the audio.
Ma'am, is it K cap?
Yes, it is K cap, but your voice is coming very low. I think when you will write, na, just check the audio settings also, because on Thursday it was fine. Okay, so this is, yes,
Okay,
this is
ma'am.
something K cap. We know at least the direction, that the direction would be a K cap, because all of these are perpendicular to each other. Now we have already seen C is equal to E divided by B. So from here we know B will be equal to E divided by C. So this will be
Mm.
6.3 divided by 3 into 10 to the power 8. That becomes 2.1 into 10 to the power minus 8 K cap Tesla. See, that's the magnetic field at this point. Okay. Using this relation, we
Okay,
got
ma'am.
the magnitude, and using the property that all of these are perpendicular to each other, we got the direction. Am I clear?
Mm. Yes, ma'am.
We'll practice more questions. First, you write down this one.
I'm done.
Okay, let's practice one more question based on this. See, this says the magnetic field in a plane EM wave is given by this 2 into 10 to the power minus 7 sine 0.5 into 10 to the power 3x plus 1.5 into 10 to the power 11 t, this much of Tesla. Okay, it says what's the wavelength frequency of this wave, and you have to calculate the expression for electric field. See, I'll write down the equation again. This says by is equal to 2 into 10 to the power minus 7 sine 0.5 into 10 to the power 3x plus 1.5 into 10 to the power 11 t. Okay. Now see, Basmi, tell me one thing, the main equation that we have already studied.
Uh, B naught
B
sine
is
kx
equal to,
plus
yes, sine kx
kx plus omega t
plus minus
plus or
B.
minus.
This is the equation we've studied. Okay, now
Yes,
it
ma'am.
says what is the wavelength. Do you realize one thing from this, that by seeing this, you have many things from here already. Like, you know, what's the
Hmm.
peak, if the question says peak value, so you will say this is 2 into 10 to the power minus 7 Tesla. This is the peak value or the amplitude. Got it?
Yes, ma'am.
Okay, tell me the value of the angular wave number.
0.5 into 10 raised to 3.
Yes. 0.5 into 10 to the power 3. Okay, this will be meter inverse. The unit of it is meter inverse. Okay, so this is the angular
Okay,
wave
ma'am.
number. Can you tell me the angular frequency?
1.5 into 10 to the power 11.
And you're still not writing the units. What's the unit here? Tell me.
Uh, um, and frequency is third, not hertz. Henry, hertz. Henry. Is it hertz?
Oh, no, hertz.
Oh, I was right to say
Not,
hertz.
yes. Henry is just for inductance. Okay, Henry term is there only for
Okay,
inductance.
ma'am.
You'll not even find it anywhere else. Okay, you
Mm,
can remember it like this. Omega is 2 pi into linear frequency. Linear frequency is hertz. Triangular will also be hertz.
yes, ma'am.
Okay. Now, first part says, let's come to the question. It says, what is the wavelength? So, how should I get the wavelength from all this?
Um,
Which quantity relates with wavelength?
wave number?
Yes,
No,
angular wave.
the omega wave
No,
frequency.
no, no, no. Angular wave number K. K relates with wavelength. Now, tell me its formula. I made you write
Ma'am,
in
I
the link.
don't know.
You don't know? Check the notes then. I think you have not gone through the notes, Basmi. Is it?
K is equal to 2 pi by lambda.
Okay, but just tell me one thing honestly. Could you just go through the notes also, or you couldn't?
I did go through the notes. I forgot about this.
Okay, you went through the notes. Okay.
Yeah.
So see, from here lambda will be equal to 2 pi divided by k. Now see, 2 pi divided by k is 0.5 into 10 to the power 3. That becomes 4 pi into 10 to the power minus 3 meters. Okay. Now it says and frequency. So how do we relate linear frequency? Frequency means linear frequency. Angular it will specify. So linear, how do we get?
Yeah. From angular frequency 2 pi nu.
2 pi, exactly. 2 pi into this linear frequency. So we say linear frequency is equal to omega divided by 2 pi. So omega is
Mm.
1.5 into 10 to the power 11 divided by 2 pi. Okay, this has to be solved. Hmm. I'm just keeping it because pi, then we'll not be able to solve it, right? We'll
Okay,
we'll
ma'am.
not. So I'm just writing 0.75 into 10 to the power 11 by pi. Sorry. This much of hertz. Okay.
Okay, ma'am.
Now it says second part says expression for electric field. Now tell me, Basmi, out of the whole data that we have right now in front of you, this whole thing, can you just tell me for electric fields expression which quantity we don't have? We'll calculate that only, the quantity that we'll be lacking with. Like for the equation expression of electric field means like this was the expression of magnetic field. We have to write the same
Yes, ma'am.
expression for electric field. So what do you think will be the same? What do you think will change?
Ma'am, can't we directly use C is equal to E by B?
Yeah, that will give you
Electric field.
now electric field what? Peak value, what will it give?
It will give the peak value of electric field.
Is that the expression?
No.
Expression means the whole equation. This is known as the expression. Okay.
Oh, like that. Okay,
So
ma'am.
so just tell me
Yeah.
when we'll have to write the expression of electric field, my question to you is, do we from all of these, whatever data you are able to see on the screen, which of
Yes,
it
ma'am.
do you think has to be changed for electric field? Or
Okay.
the other can remain the same?
Okay.
K has to change by
Uh, isn't it E not sine omega t?
it will be,
Electric field is E not sine omega t, right?
but I didn't make you write that equation. At least open the notes, Basmi, while answering. Turn the page. This is written here on the screen, so you can see from the screen. Take out the page of Thursday's class when we wrote the
Peak
expression of
value
electric.
of value of electric field. You
Exactly.
can find it by C is equal to E naught by B naught, and then you just substitute it.
Correct. See, kx and omega t, why would they change? See, when we wrote the equation, I just told you there is only one difference that comes in magnetic and electric field. That is electric field. eh, See, expression for electric field changes to magnetic field, and E naught becomes B naught. Rest of it will be the same. Okay, because this is for a single wave only. This is referring to a single wave. An electromagnetic wave is propagating. Now, by looking at this expression, just tell me one more thing, Basmi. Which axis is this on which the magnetic field is propagating on?
Magnetic field is on x-axis.
X-axis. And negative x-axis or positive x-axis?
Positive. No, negative, negative. When it's
Negative.
positive, when it's
Reverse.
plus, it's
Okay.
negative. Yeah.
Reverse. So see, this is a single wave only that is moved. A single
Mm.
electromagnetic wave that is moved. So we don't know electric field is on which axis and all, because that nothing has been mentioned, because you don't know the direction of propagation or anything. Okay. So see, what we will do, for the expression of electric field, it says magnetic field along the y-axis, By has given. But here it has clearly mentioned that the axis is x. It means it is telling about the direction of propagation. Okay. So see,
Yes,
for the
ma'am.
expression, when you write the electric fields expression, you write the expression as it is, unless the data has been mentioned. So for the wave, the wavelength will be the same. So angular wave
Mm.
number will be the same. Then frequency is what? Frequency means in 1 second how many complete cycles of waves have passed. So if one single wave is there, its frequency is something. That will be the same frequency when you're calculating for the electric field, because the wave is the same. So when frequency is the same, so your angular frequency will also be the same. Okay, see, k is a function of
Okay, ma'am.
wavelength and this is a function of frequency. Wavelength basically means the length of a wave, and frequency means in 1 second how many cycles of wave has cross. This is in 1 second fixed. Here the time isn't fixed. That we call as the time period. Okay. Now, if we
Okay,
are
ma'am.
referring to a single wave, one wave, its magnetic fields
Mm.
component will be different, peak value will be different, electric fields peak value will be different, but these things will be the same because it's the same wave. Okay. So yes, you are right.
Okay,
Here
ma'am.
we will calculate for the B part. This was the A part. For the B part, we'll have to find out the peak value. So C is equal to E naught by B naught. So E naught will be equal to P naught into C. So peak value of magnetic field is 2 into 10 to the power minus 7 from this.
Mm.
Yeah.
Yes, ma'am.
Into 10 to the power minus 7 into 3 into 10 to the power 8. That makes it
Yes.
60. Yeah, this is 60. So 60 volt per meter. That's the peak value. So here when we write the expression of electric field, peak value will be 60. Now sign. Kx, k will be the same. K was 0.5 into 10 to the power 3. K x plus was given, you write plus. Now omega t. So omega was given as 1.5 into 10 to the power 11 and this is volt per meter. Like this you get the expression. Okay.
Okay, ma'am.
First you write down the question, understand it, then you can write this question. You've got this?
Yes, ma'am.
Please write it. Just one more thing. Since it has given By is there. See, when you write electric fields expression, look, we have three things from here. X tells you about the direction of the wave.
Yes, ma'am.
Yes. So wave is propagating along the x-axis. If we write
Mm.
here, I'm writing here.
Okay, ma'am.
Direction of propagation. This is along the x-axis and along the negative axis, right? That's what we know from here.
Yes.
And it has clearly said that By is there, means magnetic field is along the y-axis. So where will be the electric field be then? Which axis?
In the z-axis.
Z-axis. So when you write now, so here just mention Ez. Okay, like this.
Oh, okay,
Okay,
ma'am.
so that it tells that you know the direction of electric field also. That
Mm.
much. Okay, please try. This is a question from your NCRT, by the way, this also.
Okay, ma'am. Ma'am, can you scroll down? Okay. Ma'am, can you I'm done.
Okay. Now let's come to another topic, that is Maxwell's displacement current. So basically, what is displacement current and all? We'll come to that later. Uh, we had Ampere's circuital law. We studied Ampere's circuital law. What was that?
Can you repeat what you said?
Ampere's circuital law. What was it?
Ampere circuital law. It was something with magnetic field, and I forgot which one it was.
It was related to magnetic field. Recall, it was
Yeah.
the formula was similar to the Gauss law. Not Gauss law,
Ma'am,
but
B
yeah,
dot DL, was it that B dot DL?
B dot dl, integral of B dot dl
DL,
is equal
yeah, it's little, not, not I
to
think.
mu naught
No, not
I.
I.
Okay.
Yeah.
Line integral
Yes,
of
yeah.
magnetic field is mu naught times the current that is enclosed. Okay. Now see,
Okay.
when Maxwell did certain experiments, what he saw, let's say these were two capacitor plates, spherical capacitors he took, and these were the two capacitor plates, and he connected them to a battery. The battery was there through the wires, and the key was connected, and finally the whole circuit was produced. Then what
Mm.
did he do in this whole circuit? The current that was flowing was I. This was the current that was flowing across this whole circuit, which is I. Now he took two planes, just two planes, coplanar planes. Let's say this is C1, and here he took one more plane as C2, just as if to enclose it. Okay. Now see, in C1 region, what happened was in coplanar plane 1 means C1, this one. It was just an area surrounded. So that Ampere, see, for Ampere circuit law, you require an Amperian loop. So this was a sort of Amperian loop that was taken. So in this region, B dot dl of the C1, the answer was mu naught I. Okay, I is the current flowing, so mu naught I. So see, this is consistent with Ampere's circuital law. This is what was the Ampere circuital law.
Yes, ma'am.
So it was consistent with Ampere's circuital law. Okay, but then see, I hope you remember when we discussed about capacitors. In capacitors, see the result, this I did. See, in capacitors, if you remember, I discussed with you that there is no flow of current here because it's a dielectric medium. So how do the charges get transferred? Here, positive charge is there. So it induces, by the process of charging by induction, it induces negative charges, and this is how the charges further travel. Remember, that's what we discussed?
Yes, ma'am. Yes, ma'am.
So here, what will happen if I choose a loop here and I want to calculate a current? I'll not be able to get the current. Yes.
Mm.
So if I take
Yes, ma'am.
in coplanar plane 2, means the second loop which we have chosen within the capacitor, what we will get if we take this will be B dot TL integral. C2 I am mentioning so that you remember. It will be mu naught into current enclosed. That will be 0 because your I is 0. There is no
Yes,
current
ma'am.
between the capacitor plates. So that, this is inconsistent now. This wasn't the Ampere circuital law, right? This it
Yes,
means
ma'am.
this whole result is inconsistent with the Ampere circuital law. This is consistent
Mm.
because current was flowing. So it means something is missing. So he did certain more experiments and it was observed. See, when we have time varying magnetic field, why do we have all these current in this circuit? Okay, battery is producing them, and what if battery is not producing them? Because of magnetic field changing, we have the current. That's what we studied
Yes,
in electromagnetic
yes,
induction.
ma'am.
The whole concept was that magnet was coming closer to the coil and galvanometer was getting deflected, means magnetic field was giving you current. So if the way I started the chapter of EMI, same thing here also. If time varying magnetic field is giving rise to current, Then time varying electric field should also give rise to current. We have studied this part in EMI. Remember, in current electricity,
Yes,
we have
ma'am.
studied I give rise to B. I will give rise to
Mm.
B, right? That by its
Yes,
avatar
ma'am.
was that a current carrying conductor was there I. So at a point, this it will give the magnetic field. That's what we studied in current electricity. But in the chapter
Yes, ma'am.
EMI, we studied that if you have a magnet and you have a coil, then it will produce a current that is known as induced current. So current will also be there. So current giving rise to magnetic field giving rise to current was there. But this time it was proved. See, when EM waves we started, I told you that if time varying magnetic field is giving rise to electric field, then time varying electric field will also give rise to magnetic field. That's what we're studying. And time varying, we have seen also
Yes,
the
ma'am.
equations, kx, omega t, and all, how it is varying with time. Yes. So if this whole is giving to a this whole thing is giving rise to current, then this electric field must also give rise to some amount of current. That's why the inconsistent equations were coming. Okay, the equations were inconsistent because the electric field which is contributing towards the current was not decided. So electric field also contributes to a current that was proved by Maxwell. And this current is known as the displacement current. What is the displacement current? When the current that comes into the system when you have time varying electric field. Due to electric field, the kind of current that is induced. The way magnetic field induces current, see the current that is induced by the magnetic field. This is known as the conduction current. Conduction current means the current which we are studying, which is contributing in the conduction in the electricity, current electricity. So this is the conduction current. This I1, this I. This is the conduction part contributing to the current.
Mm.
We said due to electric field, see between the capacitor plates, electric field is existing. Yeah.
Yes, ma'am.
So due to that, this electric field is giving rise to the displacement current. This is known as the displacement current that is existing between the capacitor plates, which was missing. That is
Mm.
not the actual conduction current which we study from the battery, because obviously if between the capacitor plates charges cannot travel, so how will there be a current? So that conduction current is not there between it. So there's a new kind of current which is induced by the electric field which is present between the capacitors. That is known as the displacement current. And it was observed that this displacement current value is epsilon naught times d phi over dt. This is the formula for the displacement current, where phi is equal to electric field into area. Okay, this phi is not the
Okay,
magnetic
ma'am.
flux. This is the electric flux. Because everything is due to
Mm.
the electric field, so you don't have any magnetic component here. This is related to your electric field. Got it?
Okay.
Now we'll see if this current is actually existing. So now we should get our answers perfect. Now there shouldn't be any problem, right? But I'm just repeating what is displacement current, first coming to its formula. See, it is that current that comes into existence in addition to the conduction current whenever electric field and flux change with time. Now this is all related to your electrostatics part. Okay, this is not related to your magnetics part. Magnetics part is this. This is the electrostatics part which we studied. So what happened? Okay, I'll repeat this at the end again. But what happened was that here displacement current is existing, which is not the usual current, the direct current which we say, or the conduction current that glows the bulb, that lightens up the circuit and flows across the resistors and all. That is not your current displacement current. That is your conduction current, which we study. But Maxwell said between the capacitors, electric field will also give rise to certain current. It will induce them. It cannot produce it, but there will be a current that comes, which was termed as the Maxwell's displacement current. Now see, we'll see how it is consistent. Now see, two kinds of, if I write two kinds, the total current enclosed will be, we'll have the conduction current plus the displacement current.
Yes, ma'am.
Both of them will be there. Okay.
Yes, ma'am.
Conduction current is also existing and displacement current is also existing. Now see, when we are talking about, so see the Amperes circuital law. Now the Amperes circuital law will be this. Now let's come to the loops separately, the loops that we were studying. Okay, let's talk about the loops that were existing. If I talk about the first loop, C1, okay, in that
Ma'am.
B dot dl, if I take B dot dl, this will be equal to mu naught the conduction current, because in that loop, displacement current is 0 and conduction current is non-zero, because in that the first loop, C1 means the first loop where the current was flowing, this one. So in this wire here, conduction current is only existing, right? There is no displacement current. So this part is fine. And we started with this only. Conduction current is there. Okay. But let's talk about the second one. If we talk about the C2, B dot dl, now see, here there won't be any conduction current. Only displacement current will be there. Because between the wires, the current cannot pass. So conduction will be 0. But we studied there is additional current, that is displacement current, that will be equal to non-zero. Yeah.
Yes, ma'am. Yes, ma'am.
So if I take this, this is, if I take the value of this, B dot dl is equal to mu naught id. Now, displacement current, I told you the formula is epsilon naught d phi over dt. Yes.
Yes, ma'am.
So see, if I'll write this here, this will be B dot dl is equal to mu naught epsilon naught d phi over dt. Will it be? Okay. Now, flux is equal to, according to Gauss law, what is the flux equal to?
Flux is equal to E
Gauss law. What is Gauss
A
law?
E something with E.
What was Gauss's law? Nothing with E. Now you're forgetting every basic law, Ampere circuital law, Gauss law. We even discussed it in all the chapters. Gauss law was coming in every chapter. Now you tell the Gauss law. What?
Is it E dot dA
That is not the Gauss
integral?
law. That is the formula of flux. Okay, that you are right. It is the formula of flux. But Gauss law wasn't this. Gauss's law was a specific line that
Oh,
we wrote. Okay,
you
try to
want
recall it through Ampere circuital law. Ampere circuital law, go reverse. Ampere circuital law is this. B dot dl is equal to mu naught I. So Gauss law will be?
is it electric flux in a closed surface and it's proportional to the charge? It's something with charge.
Okay, something
Electric
with
flux
charge
in
then.
an electric
Yes,
flux in a closed surface has a charge. It has
it has
charge, yeah.
charge. Okay, charge I have written then. Now recall.
You know Q by E naught. Is it that Q by E naught?
What is E naught?
Epsilon naught.
Epsilon naught. Electric flux is equal to charge enclosed by E naught. This is the whole
Epsilon.
formula, Q by epsilon naught. When you say E dot ds, that's the formula of flux, like magnetic flux. But law is this. You need to
Okay.
revise. You have to revise. You'll mess up with your half yearlies then.
Mm.
After the revision test and all, if you're still not able to recall, I told you the most important part of your first chapter is Gauss law. So I think I told you that just to make the derivations and the formula separately. Did you do that?
Yes, ma'am.
Till which chapter? Because I think last time current electricity you were doing. So current electricity is written.
Yes, ma'am. I still have to do the fifth and sixth chapter.
You have
Ma'am, I have to do the fifth, sixth, and seventh
so
chapter.
fourth is done. Moving charges and magnetism.
Yes, ma'am. Till the fourth chapter, it's done.
Fourth is done. Fifth, sixth. Okay. So they are short chapters. Do them. What we'll do, see, what I'll do, I'll start with ray optics. But first half of the class, we'll just have the ray optics and all. Then the second half will be your test type part. Okay, that I'll discuss so that you are prepared for after. Because this way, whatever you have studied, you will then again mess up. And that's what happens every weekly test also. You know the things, and just because of slight things, you mess up. So we'll practice. Okay, so you complete that, at least have the derivations and the formula separate with you, Basmi, so that when we revise, then it will be just easy for you to go through the notes. Okay.
Hmm. Okay, ma'am.
All right. So yes, you are right, phi is equal to q by epsilon naught. Now see, I'll put the value of phi here. So integral of b dot dl is equal to mu naught epsilon naught. Now instead of phi, so I'm putting dq over dt is there, and this epsilon naught is there. This epsilon naught will cancel themselves. dq over dt is the current. So b dot dl is equal to mu naught I. See, now is it consistent with Ampere's circuital law?
Yes, ma'am.
We are getting b dot dl is equal to mu naught I back, despite considering the second coplanar surface. It was because there was a displacement current that was existing which lagged in our answer. So this shows a consistency in Ampere's circuital law. Okay.
Okay, ma'am.
Write it till here about the displacement current and all. So I'll just quickly repeat it before you begin with it. A quick small revision about it. See,
Okay,
two
ma'am.
planes were chosen. Okay, and if you have any doubts in this, please stop me. Two planes were
Hmm.
chosen in a normal usual circuit with two capacitor plates. One was where the wire was there and the current was flowing. One was the region between the plates where no current flows. So in the first region, we could get integral of b dot dl as mu naught I because current was there. But in the second one, we weren't getting b dot dl is equal to mu naught into 0. So it showed that it means the Ampere circuital law is not valid everywhere. It's inconsistent. It's valid for some places. It's invalid for some places. So Maxwell did certain experiments and he concluded there is one additional current which we were not considering. Due to magnetic field, we were considering all the current, but due to electric field, when time varying electric field changes, and between the capacitor plate, electric field is there. So when this changes, we'll have the current also, that is known as the displacement current. So formula of this displacement current is epsilon naught d phi over dt, and this phi is the electric flux. This is not the magnetic flux. It's the electric flux whose formula is E dot A. This is the formula, okay, not Gauss law.
Okay,
So
ma'am.
total current is conduction current plus displacement current this time. Now including displacement current, we saw that B dot dl is mu naught I. That was already perfect before also. But the
Hmm.
displacement current, when we introduced it, we got epsilon naught d phi over dt as our formula. This formula you don't have to derive, you just have to remember it. When electric flux was put according to Gauss law, because electric field we are considering, so entire first chapter will be done. So we finally got B dot dl is equal to mu naught I. This meant that this Maxwell's displacement law current was only missing. Okay.
Ma'am.
All right. So this is the consistency in Ampere's circuital law. All right. Please start writing from here.
Can you scroll down? Can you scroll down? Can you scroll down? Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, can you scroll down? I'm done, ma'am.
Okay. See, so when you write the modified ampere, the question will be modified ampere circuital law. You have to be careful whether it's modified ampere circuital law or ampere circuital law. Like in the weekly test, I think I have given modified ampere circuital law. So that time I have given you marks because we didn't discuss this. But when a modified ampere circuital law comes, then you have to see integral of v dot dl is equal to mu naught IC plus ID. Okay, where ID is the
Okay, ma'am.
displacement current, IC is this, and write the formula of ID. One more thing, if capacitance is given, capacitance or voltage is given, capacitance and voltage is given, voltage are given. Then see, I displacement current is equal to epsilon naught d phi over dt. Yeah. Now see,
Yes,
flux
ma'am.
we know is equal to E electric field into area. So if I
Yes,
write
ma'am.
that, the displacement current will be equal to epsilon naught area dE over dt. Flux here, area is constant, so it will be taken out. Now, if you remember electric fields, there was a formula, electric field gradient. Electric field as a gradient of potential.
No.
You don't
No,
remember?
ma'am. There was.
E is equal to, I'll tell you, minus dV over dr. Remember we did this.
Yes, ma'am.
Okay, so this is what I am referring to. Electric field can be written as potential divided by the length, or you can say the distance. So when we put it here, ID will be equal to epsilon naught A. Now instead of E, we'll have C. D, you have, instead of E, we'll get V by D, and this dt was already there. Okay. So if I just
Yes,
rearrange the
ma'am.
terms, epsilon naught here, A here, D here, and dV over dt here. Can you just tell me which term is this? Epsilon naught A by D is
Capacitance.
the form of capacitance of parallel plates. Okay, capacitance between two parallel
Yes, ma'am.
plates, epsilon naught A by D. So C dV over dt is also one of the formula that you can use just in case if you witness any capacitance or potential. Okay. Now there are
Yes, ma'am.
basic four properties of the displacement current. Let me just tell you them. They're very easy. You'll be able to understand. Whenever a flux changes, there will be displacement current. Not only flux, when the time varying electric field changes, or your electric, because if electric field changes, electric flux will change. Remember when we did the EMI chapter, we discussed magnetic field is changing, that's why flux is changing, that's why we have induced current. Similarly, electric field changes, electric flux changes, and you have displacement current. This gives rise to displacement current. Okay,
Yes,
that's
ma'am.
the first property. Second, it produces magnetic field. Okay, more than this, see, it satisfies the property of continuity. It produces magnitude is equal to rate of displacement one from one capacitor. See, more than it produces magnetic field, no? I'll write. It is not an actual current, okay? It is
Ma'am.
not an actual current. This is just coming in your system because electric field is inducing a current. So displacement, that's why its name has been given as current, displacement current. It's not a real current. I hope you get it. It's not a real current. And see, magnitude
Yes,
of
ma'am.
displacement current is equal to the rate of displacement of charge from one plate to another plate. So see, between the capacitor plates, if whatever are the charges flowing, if this charge is more, displacement current will be more because it's these charges only, these electric field. This charge is giving rise to electric field, which is giving rise to flux, which is giving rise to displacement current. So if this is more, see if your Q is more, the electric field will be more. Electric field more,
Yes.
flux more, electric flux more, displacement current will be. Okay, that is the third.
Okay, ma'am.
And finally, it says as it satisfies the continuity property of continuity. This means, see, in your circuit, the current was coming till here. There wasn't any current between the plates. Okay, there was a discontinuity over here. It now here also you have a displacement current that is acting, so a property of continuity is satisfied. Okay,
Yes, ma'am.
quickly copy down this also.
Okay, ma'am. Ma'am, please hold up. Ma'am, can you scroll down? Ma'am, can you scroll down? Done, ma'am.
Okay, let's see some questions then from here. This is a parallel plate capacitor has has circular plates, each of radius 5 centimeters. This is a question from your NCRT only. It is being charged so that electric field in the gap between the plates rises to a steady rate. Now, rate of electric field means you have dE over dt. Okay, rate means it's not electric field given. Look at the unit, volt per meter per second. Okay, so electric field divided by time. So this is 10 to the power 12 volt per meter per second. Rate of electric field means this is getting divided by time. Okay, pay attention to the units and start writing the units. Your marks will be cut in the exam, final exam, board exam. Okay, units are important. That's why whenever we do a topic, I write that it's SI unit. So whatever is your final answer, you mention its unit. Oh, I had to discuss the assignments with you today, no? Okay, I'll discuss them in the next class. So radius is 5 into 10 to the power minus 2 meter. Now it says what's the displacement current. So what did we discuss? The displacement current is epsilon naught d phi over dt. Flux can
Yes,
be
ma'am.
written as flux can be written as E dot A. So this becomes area dE over dt, the step which we did here. We have
Yes,
done
ma'am.
this dE over this one. Okay, and dE over dt is given to you. Epsilon naught is 8.85 into 10 to the power minus 12. Area will be pi r square, so 5 into 10 to the power minus 2 whole square. dE over dt is already given to us as 10 to the power 12. So whatever you get, ampere would be your displacement current. Okay.
Okay. Okay, ma'am.
Write down this question as well.
Ma'am, can you scroll down? Ma'am.
Okay then. When do you want the next class? Tomorrow?
So, ma'am.
Let's have the class tomorrow and Monday at least. So 2 consecutive classes we'll get. I'll discuss the electromagnetic spectrum with you. You will be receiving